To understand electricity, you first have to understand atoms. They're the basic building blocks for everything that exists in the universe. All matter is made from a combination of atoms.
Matter is any substance that has mass and occupies space. Matter can exist in three forms: solid, liquid, or gas. Atoms are composed of three primary particles: the proton, the neutron, and the electron. Protons have a positive charge, neutrons have no charge, and electrons have a negative charge. The proton and neutron form the nucleus or center of the atom, and the electron orbits around the nucleus. If you want to understand atoms, you need to start with two fundamental laws or principles. One is the law of charges, which simply states that unlike charges attract and like charges repel. Since the proton has a positive charge and the electron has a negative charge, they are attracted to each other. In theory, all the electrons would fall into the nucleus of the atom because of its net positive charge, except for the second law concerning atoms.
The second fundamental law or principle that applies to atoms is centrifugal force, which is what causes a spinning object to pull away from its center or axis point.
Electrons do not fall into the positively charged center of the atom because they are spinning around it. Centrifugal force prevents the electrons from falling into the nucleus of the atom. So there's a balance between the law of charges pulling the electron toward the proton and the centrifugal force pulling the electron away from the proton. Although atoms may contain multiple orbits or shells, it is the electrons located in the outermost orbit that are important in the study of electricity. This outermost orbit of an atom is known as the valence orbit. Any electrons located in this outermost shell are called valence electrons. The maximum number of electrons that can be located in the valence shell is 8, regardless of how many shells or orbits the atom may contain. Valence electrons are more important to the study of electricity because they are the most loosely held by an atom and can be given up to produce current flow. If another electron should strike the orbiting valence electron, the energy of the striking electron is given to the orbiting electron. The orbiting electron moves off to strike another electron, and the striking electron settles into orbit around the nucleus of the atom.
Conductors, like this copper wire, are materials that electric current can travel through easily. The atoms of most conductors contain 1 or 2 valence electrons. Atoms normally want the valence orbit either completely full with a maximum of 8 electrons or completely empty. Atoms with only 1 or 2 valence electrons will readily give them up to produce an empty valence shell. The best natural conductor is silver, followed by copper, gold, and aluminum. Silver, copper, and gold all contain 1 valence electron. Aluminum contains 3 valence electrons. Insulators are materials that do not conduct electric current. Insulator materials are things like dry wood, plastic, rubber, varnishes, and mineral oils. Insulators are generally made from compounds that have a very stable molecular structure. Electricity has standard numerical values that you need to understand if you want to work in the electrical field. The ampere or amp is a measure of the actual amount of electricity flowing in a circuit.
The ampere is a rate of flow. It's similar to measuring the amount of liquid that flows through a pipe. 2 factors must be considered when measuring flow: quantity and time. There's a big difference between a flow rate of 1 gallon per minute and 1 gallon per second.
Voltage itself does not flow through the circuit. Voltage is the force that pushes the electrons through the circuit. It's the electrons that flow, not the voltage. A good analogy for voltage is to think of water flowing through a pipe. Voltage is like the water pressure, and the electrons being pushed through the circuit are like the flowing water. In fact, voltage is often called electrical pressure or potential difference.
A standard receptacle outlet contains voltage or potential between the 2 main conductors, but there is no current flow until the circuit is completed by connecting a device that allows current to flow.
The ohm is the unit of resistance to current flow. Resistance hinders the flow of electrons through the circuit. A good analogy would be the resistance you feel when you're in a pool or the ocean up to your chest in water and you're trying to walk. Electrical resistance is much the same way. The greater the resistance, the greater the hindrance to the flow of current.
A resistor in an electric circuit can be compared to a restriction in a water system. The reducer limits the flow of water through the system, just as a resistor limits the flow of current through an electrical circuit. Wattage is a measure of the amount of power that is being used or consumed by the circuit. Electricity is a form of pure energy. Energy cannot be created or destroyed, but its form can be changed. Watts is a measure of the amount of electrical energy that is being converted into some other form. An electric range converts electrical energy into thermal energy. An electric motor converts electrical energy into kinetic energy. The amount of energy supplied to a device is proportional to the flow rate and the pressure. For instance, the amount of turning force produced by a turbine is proportional to the amount of water supplied to the turbine blades and the pressure of the water. Electric power is basically the same. The amount of watts or power is proportional to the amount of current flow or amps and the pressure, voltage, being used to push the electrons through the circuit. If the lamp is replaced with another lamp that offers less resistance to the flow of electrons, the flow rate will increase, causing more electrical energy to be converted into more light and heat. Another common measurement of energy is the BTU, or British Thermal Unit. 1 BTU is the amount of heat necessary to raise 1 pound of water 1 degree Fahrenheit. The BTU is often used to measure the cooling capacity of air conditioning equipment, or the heating capacity of a heating system. 1 watt is equal to 3.412 BTUs per hour.
Since electrical values of voltage, current, and resistance are standard for everyone, these values can be used in mathematical formulas. The first person to establish this relationship was a German scientist named George S. Ohm. These laws concerning electricity are known as Ohm's Law, which is the basis for almost all electrical calculation. From his experiments, Ohm proved that in a DC circuit, the current is directly proportional to the voltage and inversely proportional to the resistance. Ohm's experiments resulted in mathematical formulas that we use to calculate different electrical values.
In Ohm's law formulas, the letter E is generally used to represent EMF, or voltage. The letter I is used to represent the intensity of current, or amperes, and R is used to represent resistance. There are 3 basic Ohm's law formulas. Voltage is equal to the current flow times the resistance, or E equals I times R. Current flow is equal to the voltage divided by the resistance, or I equals E over R. And resistance is equal to the voltage divided by the current, or R equals E over I. A simple chart can help you remember these formulas. If you're trying to find the voltage and you know the current and resistance, place your finger or thumb over the letter that represents voltage, in this case E. The chart indicates that you should multiply I by R. If you are trying to find the current, place your finger or thumb over the letter I. The chart indicates that you should divide E by R. If you are trying to find the resistance, place your finger or thumb over the R. The chart reminds you to divide E by I. Assume that a 24-volt battery is connected to a resistor. Also assume that an ammeter indicates a current flow of 1/2 ampere. What is the resistance of the circuit? After determining the proper formula, substitute the values in the problem for the letters in the formula. The letter E is replaced with 24 because the battery has a voltage of 24 volts, and the I becomes 0.5 because the circuit current is 1/2 amp. The formula indicates that the resistance can be determined by dividing the voltage by the current. 24 volts divided by 1/2 amp equals 48 ohms. So the resistor has a value of 48 ohms. The symbol after 48 is the Greek letter omega. Omega is used to represent ohms in electrical formulas. Assume that a 36-volt battery is connected to a 144-ohm resistor. How much current will flow in this circuit? After determining the proper formula, substitute the values in the problem for the letters in the formula. The letter E is replaced with 36 because the battery has a voltage of 36 volts, and the R becomes 144 because the resistor has a value of 144 ohms. 36 divided by 144 is 0.25. There is a current flow of 0.25 amperes in this circuit. Assume that a circuit has a current flow of 2 amperes when connected to a 30-ohm resistor. How much voltage is applied to the circuit? Again, the formula chart indicates the correct Ohm's Law formula to determine this voltage. Since the letter E represents voltage, cover the letter E in the chart. The chart indicates the formula E equals I times R. Substitute the circuit values for the corresponding letters in the formula. The letter I becomes 2 because there is a current flow of 2 amperes in the circuit, and the letter R becomes 30 because the resistor has a value of 30 ohms. Multiply 2 amps times 30 ohms. The answer is 60 volts. A more complete chart showing formulas used to determine values of voltage, current, resistance, and watts can also be used. In this chart, the letter P represents watts. The letter P stands for power.
There are 3 rules that can be applied to series circuits. We can determine the values of voltage, current, resistance, and power for each circuit component by using these 3 rules in conjunction with Ohm's Law.
First, the current is the same at any point in the circuit. The total resistance is the sum of the individual resistances, and the applied voltage is equal to the sum of the voltage drops across all the circuit components. Consider this first rule of series circuits, that the current must be the same at any point in the circuit. In a complete circuit, electrons will leave the more negative source of power and flow to the more positive source. Imagine electrons leaving the negative battery terminal, flowing through each resistor, and completing the circuit back to the positive terminal. Since there is only one path for current to flow from the negative to the positive terminal, the current must be the same at any point in the circuit.
The second rule concerning series circuits is that the total resistance is the sum of the individual resistances. A simple way to express this rule is to say that resistance adds or accumulates in a series circuit. Since a series circuit contains only one path for current flow, the current is hindered by each resistive element in the circuit. The third rule concerning series circuits states that the applied voltage is equal to the sum of the voltage drops across all the circuit components. Recall that voltage is electrical pressure. Voltage drops in an electrical circuit are similar to pressure drops in a hydraulic system.
Parallel circuits are characterized by the fact that they have more than one path for current flow. Assume that current leaves the negative battery terminal. Part of the current will flow through resistor R sub 1. The amount that flows through resistor R sub 1 is determined by the resistance of the resistor and the circuit voltage. The remainder of the current flows to resistor R sub 2 and R sub 3. Part of the current will flow through resistor R sub 2, and the remainder will continue to resistor R sub 3.
There are 3 rules concerning parallel circuits. When you employ these rules with Ohm's law, you can determine the electrical values of voltage, current, resistance, and power for all elements of the circuit.
First, the voltage is the same across all branches of the circuit. The second rule is that the total current is the sum of the currents in each branch. And the third rule is that the reciprocal of the total resistance is equal to the sum of the reciprocals of the resistance of each branch.
Consider the first rule concerning parallel circuits, that the voltage is the same across each branch. Using a voltmeter, we see that the circuit voltage is the same across each branch of the circuit.
Since the voltage is the same across all branches of a parallel circuit, the lights in a building are connected in parallel. Receptacles are connected in parallel so that any device connected to them will have the same voltage.
The total current of a parallel circuit is the sum of the currents flowing through each branch. This can be seen by measuring the current through each branch and then measuring the total circuit current. To recap, a series circuit is a circuit that has only one path for current flow. We discussed the three rules concerning series circuits.
First, the current is the same at any point in the circuit. The second rule states that the total resistance is the sum of the individual resistors. The third rule for series circuits states that the applied voltage is equal to the sum of the voltage drops across all the circuit components. Parallel circuits are circuits that contain more than one path for current flow. There are three rules concerning parallel circuits. The first rule concerning parallel circuits states that the voltage is the same across all branches. The second rule states that the total current is the sum of the currents in each branch. The third rule concerning parallel circuits states that the reciprocal of the total resistance is equal to the sum of the reciprocals of the resistance of each branch.
This series continues in our next segment on electric meters, basic components, and symbols.